Here we go. Perfect. So what we want to work on right now is we want to work on chapter 15 and 16. At the end of chapter 15, you're going to have a test or a chapter test. It's going to be one of our 6 tests. This part of the unit is going to take about 2 weeks. But the problem is 2 weeks from now, we have like a big 1 week break, right? So we're going to work hard for 2 weeks, and then you're going to get a week off. And then we're going to come back and we're going to do review on Monday and test on Tuesday. And that's super cruel. And that's me being a jerk. And I apologize sincerely, but there's no other way to do it. So it's just the way it's got to work. So we're going to talk about equilibria. And equilibria are reactions that are reversible. They can go in the forwards direction, but they can also go in the reverse direction. Now we have to kind of learn a little bit about chemical equilibria. We have to learn a little bit about testing chemical equilibria first. So chemical systems or chemical reactions are much easier to study when they're in a closed system. That's a bolded term. It's a term you are required to know. A closed system is when substances involved are physically separated from substances that you don't want to study. So what that means is that if you care about a chemical reaction happening, what you want to do is you want to separate them from other chemicals that you don't want to study. So let's take a look at this pop bottle on the side here. The bottle on the right contains a soft drink. Would you consider it to be a closed system? So is this a closed system? Are the substances inside physically separated from the substances outside? They are right now. How can you turn this closed system into an open system? Jaden. Open it. And you've done that before, right? What happens when you buy a pop bottle or you buy a pop can or something like that and you first open it for the first time? Right? Everybody should be relatively familiar with that sound. And so, yes, the lid keeps all of the chemicals inside the container. So they're trapped. This is the idea behind a closed system. An open system is where matter is allowed to exchange between the inside and the outside of a container. There's a third system. I don't know if anybody's aware. There's an open system, there's a closed system, like those are 2 systems that we can have. And there's a third type of system. Ooh, no. It's just with an I.
Isolated system?
It's an isolated system. And an isolated system is where matter cannot exchange, so it's a lot like a closed system, but an isolated system is also something where energy can't be exchanged as well. You can't add energy and you can't take away energy. This is not an isolated system. We'll talk about isolated systems a little bit later on. Okay, all right. So a dynamic equilibrium, again, bolded term, something that we have to know, is established when 2 opposite processes are occurring at the exact same rate. In every closed, like unopened pop bottle, a dynamic equilibrium has been reached. This is an example of a chemical reaction equilibrium. Let's draw what's going on inside a pop bottle. So you've got a certain amount of liquid, and I know that this is stupid, right? The level of water should be significantly higher, but I'm not a good artist, so you got to work with what you got. So what's going on inside this pop bottle? Well, you got a bunch of sugar water down here, a bunch of really gross, unhealthy sugar water, but also what's been added to this container? A lot. I mean, not like a metric ton, but a lot of it. Jaden? A lot of carbon dioxide. What they do is they pressurize a bunch of CO2. The CO2 can dissolve, and when it dissolves, it reacts with the water. what I want you to do is I want you to pull out your data booklet for me, please. It's kind of weird, but I want you to go to the acid-base table, page 8 and 9. When you go to the acid and base table on pages 8 and 9, on the side you see all of the names of all of the acids, and everything's pretty similar, whatever, something acid, something acid, something acid, something ion, something acid, whatever. But there's one thing in here that should stick out, because they're giving you a little bit of extra information. They actually give you a chemical reaction. Do you see the chemical reaction? Yeah. The carbonic acid. Carbonic acid is carbon dioxide and water mixed together. When they mix together, they react to make carbonic acid. And so what we have inside our bottle is as soon as the carbon dioxide dissolves, it doesn't necessarily dissolve as carbon dioxide, it turns into carbonic acid. Now, inside this bottle, okay, you've got some carbon dioxide molecules above the level of the water. And are those carbon dioxide molecules just staying still the entire time? Are they just hanging out above the level of the water, not doing anything? No, they're crashing around. They're bumping off the side of the... I was really hoping that wouldn't happen. They're bumping off the side. They're bumping off the side of the bottle and they're crashing into the water. And every once in a while, it hits the water. Whoa. It strikes the water in such a way that it's able to dissolve. And at the moment it dissolves, what does it turn into? It turns into H2CO3. Because it just combines with the water. Okay. So we know that the carbon dioxide, these carbon dioxide molecules, they're constantly crashing into the sides, but they're also constantly dissolving into the water. Now that's not the only process that's happening here. The carbon dioxide can dissolve, but also the carbon dioxide can, this is going to sound stupid, but it can undissolve. That's not a scientific term. I'm just trying to make sure that we understand ourselves. These carbonic acid molecules, if you give the carbonic acid a little bit of energy, what happens to molecules when you give them a little bit of energy? So the carbonic acid molecules, are they just hanging out inside the solution of water? No, they're moving around, they're crashing around. And if you give them a little bit extra energy, they can decompose back into the water and carbon dioxide. So can you see how there are two very opposite processes happening here? One of them is the carbon dioxide dissolving, and one of them is the carbonic acid turning into carbon dioxide. We can express this using a chemical reaction. CO2 gas plus H2O liquid. And this is the first time we're going to use a double-headed arrow. You might have used this in Chemistry 20, depending on who your teacher was. That's the way we write our double-headed arrows. Now, if you want to do this, if you want to write like this, that's perfectly fine. It just takes more time, and I'm lazy because I'm a chemist, okay? So I'm lazy, and I want to use that arrow. But it's whatever you want. So the carbon dioxide and the water, they're combining to turn into carbonic acid. H2CO3. What's going to happen to this solution? What's going to happen to this mixture or this equilibrium the moment I take the cap off? What's going to happen to something in here the moment I take the cap off, Isaac?
Carbon dioxide is.
Would you agree that the carbon dioxide is now free to leave this bottle? And so if we have the carbon dioxide free to leave, then one of these processes is going to stop happening. Do you agree with that? There's a process where the carbon dioxide is reacting with the water, and where it's kind of unreacting, the reverse process, and turning into carbon dioxide. As soon as you open this bottle, the carbon dioxide leaves, and you no longer have both processes happening. So would you agree we need a closed system in order to trap all of the matter that we care about inside this reaction? So a closed system is necessary. I don't know how to spell necessary. Is that how you spell it? Yeah. So a closed system is necessary to keep all the matter trapped inside this bottle. If we didn't have a closed system, matter could leave and we would no longer have equilibrium. And we're gonna talk about equilibrium later. We're gonna understand more fully the ideas of equilibrium. This is a chemical reaction equilibrium. This is where we've got a chemical reaction, two things reacting, turning into something that didn't exist beforehand. Would you agree when carbon dioxide and water combine, they are no longer carbon dioxide and water? Would you agree with that? That's a chemical reaction. Two things combining to turn into something new. That's a chemical reaction. That's not the only type of equilibrium. Remember, a dynamic equilibrium is when you've got two opposite processes happening at the exact same time. That's a chemical reaction equilibrium, but that doesn't have to be the only type of equilibrium. We can have solubility equilibrium, and we can have phase equilibrium as well. So, solubility equilibrium. This is a beaker. That's the best I can do. We have equal rates of dissolving and crystallizing. So we've got a solution. And in here, I'm going to draw a crystal of some sort of a solid. So we've got some sort of solute, and we've placed the solute inside the solvent. Think of like sodium chloride in water, salt in water, right? Do you think at some point in time you're going to be able to hit a point where you cannot pack any more sodium chloride into this water? So at some point in time, it's going to stop dissolving. Would you agree with that? Yeah, you can't dissolve an infinite amount of sodium chloride into water, right? But there will be a little bit of salt, and that salt is going to be moving around. These are arrows, if you can't tell. Now, the salt that's dissolved and the salt that's in the crystal, they're not just staying still. There's a reason why I've kind of said that multiple times. These molecules, are they static, are they unmoving, or are they dynamic? Are they moving around? They're dynamic, okay? So what's happening is that these salt crystals, these salt solutes, are attracted to the salt crystal. So one of them might enter the crystal. It might precipitate or crystallize onto the crystal. We can maintain an equilibrium. We can maintain an equilibrium as long as for every one ion that joins this crystal, what has to happen? One ion has to leave. So this is what we mean by equilibrium. Did the crystal get bigger or smaller, or did it stay the same size? It stayed the same size. So that's equal. It's equal to the size that it was before. It's the exact same as it was. But are all of the particles the same particles that were there before? No. It's like, imagine we have a classroom full of 32 people, like we do right now. We've got a class full of 32 people. And as soon as the bell goes, all 32 people exit. I can maintain an equilibrium in this classroom if all 32 people exit, as long as what happens? 32 people enter. As long as the rate of people leaving and the rate of people entering is the same, we've maintained an equilibrium. Is it the same 32 people in this classroom? No, so it's not a static equilibrium, but it's a dynamic equilibrium. At the end of the day, and don't take this the wrong way, at the end of the day, it doesn't really matter who's in the classroom. The Alberta government, as long as there's 32 people in my classroom, they're okay with that, okay? So this is a solubility equilibrium. Can you understand how this substance is dissolving and crystallizing at the exact same time? So this process is dissolving, and this process is crystallizing, and they're happening at the exact same time, but we're maintaining equilibrium. The crystal isn't getting bigger, it's not getting any smaller, it's whatever. Let's talk about a phase equilibrium. Now, what do I mean by phase? Does anybody know what that means? Yeah. Phase means state of matter. What are the three main states of matter that you know of? Solid, liquid, gas. There's plasmas. Yeah. There's supercritical fluids. There's all sorts of crap, okay? But that's fine. We'll talk mostly about those three traditional phases. So imagine you've got a beaker of water. And we've got particles of water inside this beaker. Now, I need you to understand, are these molecules just sitting there not doing anything? No, they're moving around, right? If you left this glass of water, I want you to really think hard about this. If you left this glass of water there for 5 months and you came back, so you left it in your house, you went on vacation for 5 months and you came back, what would you see inside the glass? Don't say it out loud. Think to yourself.
Does it have a lid?
What?
Does it have a lid?
Did I draw it with a lid? But that's a good question, Isaac. Okay, does anybody know what are you gonna come back to here? Jaden?
Less water.
Less water. is the most accurate statement you can make. You can't necessarily say no water, but you come back to less water. Why? Why would the level of water be less 5 months from now than it is right now? Would you agree some of these molecules are slowly evaporating? Would you agree with that? Not all of these molecules inside this beaker have the same amount of kinetic energy. Some of them have more and some of them have less. Now, the molecules that have more kinetic energy, the molecules that have more kinetic energy, they have enough energy to escape the attractive forces of its partner water molecules. So this thing can leave. And then slowly over time, that one can leave, and that one can leave, and that one can leave. And eventually, the water level is going to get so low that there's just no water left in here. Eventually, if you gave it years or whatever, months or something like that. Now, we're going to do the exact same thing, except we're going to put a lid on here. Ugh, that's not how you spell lid. Perfect. So now I put a lid on here. Ooh, that's interesting. What's going to happen now?
Water will.
Is water still going to evaporate? Would you agree some of these water molecules, they still have enough energy to leave the water? But can they leave our system now? We've got a closed system. So now, this water molecule, it leaves. And if it ever loses a little bit of energy, what will happen? It'll condense back into the water. Does that kind of make sense? Do you see the two opposite processes that are happening right now? What are the two opposite processes? What do you call it when a water molecule leaves its friend water molecules? So it turns from a liquid into a gas. Evaporation. What do you call it when a gas turns into a liquid? Condensation. So we've got these water molecules. They'll leave, and that's called evaporation. But also, some water molecules will return back into water, into its liquid form, and that's condensation. We reach equilibrium as soon as, for every 5 water molecules that leave, 5 enter. That's how we define equilibrium, is identical rates of 2 opposite processes. Are we kind of okay with that? Okay. Keep in mind a closed system is needed for all equilibria. So what I want to do is I want to head into the lab here, and I want to do a lab. Now, I haven't put you in lab groups, and the reason why I haven't put you in lab groups is just over the last 24 hours, we've had 3 people either enter or leave our roster. I don't really want to make lab groups until kind of at least after the first week, okay? So you're just going to put yourself, you're going to put yourselves into groups of 2 or 3, if that's okay. And I know that I'm putting some of you in an awkward position because maybe you don't know anybody in the class or something like that. Just, I'm asking you to put yourself in an uncomfortable position, and please try here in a little bit to get yourself into a group of 2 or 3. There's 6 of those. 9 of those. So what we want to do, we would like to perform a reaction that involves an equilibrium. So what's going to happen is you're going to need all of these materials. We are at the lab bench that's directly outside my classroom, the Chemistry 2 lab bench. You're going to have to get all of these materials, and then you're going to have to perform this procedure. I want to be very clear. The vast majority of these materials, like glassware and stoppers and things like that, and the beakers, can be found on the side lab cabinets. Okay? If you don't know where something is, you can ask me, and that's totally fine. What I want you to do is there should be a couple people in your lab group, right? So what one person can do is one person can collect the potassium hydroxide and the glucose. Our glucose is labeled dextrose. That's like one of the names for glucose is dextrose, so it's labeled dextrose. So you're going to gather them in your 2 separate 50 milliliter beakers on an electronic balance. The balances are on the other side of the lab. They're in cabinets with shutters that I will roll up. And I want you to just try this out. Collect tap water, just tap water, right, as long as it's not more than 30 degrees, and perform this experiment. If you have any questions, let me know. But don't be mad at me if I say, I don't know, what does your procedure say? That's probably going to be my answer to at least half of your questions. Because somebody might ask me, how much of this are we supposed to add? And I'll say, I don't know. How much does your procedure say? Okay? I want you to really focus because the vast majority of the information should be in here. Is that okay? Yeah. Couple things. You're going to be putting everything into a flask, and then you're going to be putting a stopper on that flask. And then you're going to be shaking things up. Now I want to be very clear. Because you're using potassium hydroxide, does anybody know what classification of compound potassium hydroxide is? It's an ionic hydroxide. This is a base. This is one of the strongest bases that you can work with. And you're adding a significant amount of strong base. This is going to be a really basic solution. So you definitely need to wear glasses and you definitely need to wear aprons, okay? Now when you're shaking up the solution, the one thing I don't want to see is somebody push the stopper on and then shake it up but not holding the stopper on. This is because you're making an alkaline solution, a basic solution, and basic solutions are slippery. And if you're shaking it up and the stopper pops off, well then you're going to shake up and you're going to spill base all over yourself. Okay, please don't do that. So when you're shaking up your sample or your solution, just put one hand on the stopper and one hand on the bottom and just shake it up. Are we okay with that? So just follow the procedure, and then when you're done in the lab, you're just going to clean up and you can head back in here.